Hello and welcome to section 3.9 on the derivative of logarithmic functions. In this video, we will discuss logarithmic functions and their properties. We will leave calculating the derivatives for class. Logarithms are the function inverse of exponentials. Exponential functions require a positive number b as a base, and are of the form y equals b to the x. Given an exponent input x, the exponential output b to the x is given. If b equals 2, the exponent 5 receives an output 2 to the 5th, which is 32. Logarithms invert this process. For a positive base b and an exponential b to the x, the logarithm returns the exponential x. The logarithms were introduced by the Scottish mathematician John Napier in 1590, which ushered in the popularization of the decimal system for real numbers. The decimal system relies on viewing digits as powers of 10. Log base 10 of 100,000 is 5. Log base 10 of 1 over 100,000 is negative 5, as it can be written as 10 to the negative 5. So we represent 1 over 100,000 with the number 1 with 5 zeros between it and the decimal place. Logarithmic graphs are reflections of exponential graphs about y equal x, since logarithms and exponentials are function inverses. The domain of the logarithmic function results from the range of the exponential function. So the domain is restricted to the open interval 0 to infinity. Since exponentials have a horizontal asymptote y equals 0 as x approaches positive infinity, the logarithm function has a vertical asymptote at x equals 0. The function approaches negative infinity as x approaches 0 from the left. Euler's number e was introduced due to exponentials. It is the unique number base for which an exponential function crosses the y-axis with a slope of 1. Since e is special among bases, the logarithm base e, called the natural logarithm, is often used, and it is shortened to ln of x. Exponentials have a very quick y growth. For base 2, the value increases from 2 at x equals 1 to 32,768 at x equals 15. Logarithms base 2 increase from 1 at x equals 2 to 15 at x equals 32,768. Since logarithmic growth is slow, very large numbers can be represented using very small numbers. Logarithms show up in a number of scientific measurements. For example, decibels measure sound intensity on a scale based upon base 10 logarithms, where the sound intensity of rustling leaves can be scaled at 30, and the sound of a chainsaw is scaled at 110. That is, a chainsaw is 10 to the 8 times louder than the rustling leaves. The energy of an earthquake is based upon logarithm based 1000. A 7.0 earthquake is 1000 times more powerful than a 5.0 earthquake. The pH scale for acidity measures the concentration of hydrogen ions in moles per liter, with a scale based upon logarithm base 1 over 10. An orange has a pH of 3.4, and human blood has a pH of 7.4. So an orange has 10,000 times the concentration of hydrogen atoms than human blood. Since logarithms are inverses of exponential functions, the logarithm base b of b to the x is just x. And for positive values of x, b to the logarithm base b of x is x. This property leads to three important functional properties of logarithms. The logarithm of a product x times y is the sum of the logarithm for x and the logarithm of y. The logarithm of a quotient x over y is the difference of the logarithm for x and the logarithm for y. The logarithm of x to the power of y is the product of y and the logarithm of x. These rules follow directly from the inverse properties. Let capital R equal log base b of x, and capital S equal log base b of y. Inverting these equations gives b to the r equals x, and b to the s equals y. So the log base b of the product can be written as the log base b of b to the power of r plus s, which simplifies to r plus s, or the sum of log x and log y. The log base b of x to the power y can be written as the log base b of b to the power y times r, which simplifies to y times r, or the product of y and the log of x. These properties will prove to be extremely useful for calculus. Differentiating this logarithm function would require the chain rule, and the derivative of the inside function would be a mess. If we decompose the expression before differentiating, using the product property, the quotient property, and the power property for logarithms, then we obtain an expression which is much easier to differentiate. The second part of the chain rule is simple for each part of the expression. In class, we will calculate the derivative of log base b, and we will use logarithms and their properties to calculate the derivative of functions with variables in the power and base, such as x to the x, or arctan of x squared, all raised to the square root of x cubed minus 1. You've seen the basics, now gain mastery through practice and study.